Hello everyone. Today I'll be talking about the Navier-Stokes equations, and it's my first try on a more academic topic. So, yeah. Okay. Why am I doing this? For an essay we have to study this, and I have to say it's quite hard to learn, and some of the sources are quite dubious in some sense, and it's quite complicated in other ones that is more correct and informative. This is actually an extract from my essay. I modified some of the stuff. So the essay is originally on color modeling, so you may see some of the hints that can relate to modeling. Just excuse that. And this stuff is at least pretty much, to the best of my knowledge, correct. And if I'm wrong, do correct me as soon as possible, because I will submit it a few days later or something. Anyway, I'll start. So let us give the expression of the Navier-Stokes first, because you couldn't study something without knowing what it is. And these are the most common set of equations you'll find if you just search up Navier-Stokes online. Wait, I think I spelled it wrong. Navier-Stokes equations. And I spelled it correct. Yeah, just don't mind. It's pronounced Navier-Stokes, and it's kind of quite confusing. So yeah, they'll give you this, and this is somewhat wrong. They didn't even say that the conditions and stuff, and that's what I mean by dubious. It's quite misleading. Okay, so this set of equations make several assumptions, and they didn't even clarify. It's outrageous. Anyway, the fluid is incompressible, the fluid is Newtonian, the fluid is isothermal. So the third one is actually, in my opinion, the least important. Where the ones we're actually concerned with is the first and second. So use the fluid velocity vector, P is the fluid pressure, rho fluid density, nabla square Laplacian operator, nabla divergence operator, F external or body forces. Actually, it's more accurate to call it body forces. I'll modify that afterwards. And mu is the viscosity. Right. So for the node F can be broken down to consider many forces, including gravity and electromagnetic forces, multi-divergence forces, and I missed column forces here. Okay, so if we're considering plasma, because plasma is a fluid, plasma has density, so plasma flows from high density to low density. So plasma is also charged, as we all know. So if plasma is in a let's say a magnetic field and is moving, then you have V and you have B, so it will produce, and you have charge, you have Q. So F equals BV F equals QV times B. So they will experience Lorentz force in that sense. And if it's in a magnetic field, if it's in electric field, then it will experience column forces, depending on the electric field strength. Yeah, but that's for another day. F equals EQ. I'll just give the expression here. So NSE can be combined with Maxwell's equation in the study of magnetohydrodynamics. So this was from a YouTube video, but our studies here, anyways, is quite interesting. You can go search it up. It's in the modeling stars. Yeah, I covered that because, again, this essay is on modeling. So let's start with the physical derivation of the NSE for a better understanding of this. Yeah, it can be broken down and stuff, and so these ones I'm covering here is the short one here, the very friendly looking equation, and what it says is basically, in the case that is Newtonian and incompressible, mass and energy cannot be destroyed locally. So what it's saying is that you couldn't have velocity popping out of nowhere. So for divergence, you can look at 3 Blue 1 Brown's video. I think is somewhere in vcubingx video on Navier-Stokes. It's quite good. You can go look at that. It's one of the more useful videos I watched to make this. Like in this one, so the fluid it's assuming that the fluid is incompressible, but like it's the divergence of the velocity vector. So if I have a compressible fluid, then like I can have like maybe a compressed part here and an incompressed part here. So I can't draw, but like you get the idea. So the velocity will just go this way, this way, this way, and just go up. This divergence will be positive. So this doesn't make sense. But if it's like incompressible, then it's another story. Okay, so we will now give the more general expression. So it looks like this. It's quite easy to understand, but like so this one is the rate of change in density. So because if it's incompressible, the rate of change in density is like 0, because the del T is 0. So del T is like literally irrelevant. So nabla times rho u. So like this one is dot multiplication is quite tricky because it's well with vectors. So we can also like go circular if we don't know what the dot product and the cross product each mean in vectors. And okay. So for p being constant, there's no change in density since since rho is non-zero. Okay, so this one is just basically the incompressibility. So you just give this in the case that it's incompressible. So like this one is just basically expanding U for matrices to cover the vectors and 3D Euclidean space. Okay, so now is for the more trickier one. Actually, it's quite easy to understand if you look deep enough into it. So it's the long one, the very complex looking one. You can frighten your friends in primary school or secondary school with it, and you will say, I know the Navier-Stokes, blah blah blah. And they will be like, yeah, but no, don't. Just keep it to yourself and just teach them if they need. And I don't think they understand it anyways, but yeah, let's just start with several well-known results. So the continuity equations, conservation of momentum, conservation of mass, and Newton's second law. This one is the most important. So like we start with this. So this is the root. This is the how to say the cause of all the evil. On the root. Yeah. Okay, so we start with F equals ma. So since we're dealing with individual points, I think I forgot to mention that earlier. So the Navier-Stokes equation describes the trend of a fluid at a certain point, not the whole, like the fluid body, which will consist of like infinitely many points we're talking about, but like this one's an ideal case. Because in chemistry, I know that molecules have like molecules are not like an arbitrarily small points, which we're talking about here, but like come on, it's close enough. Physics isn't real life. Yeah. Okay, so for us, this equation can be transformed into this. So because p we just m we just replace it with phi. And du over dt, this one is the acceleration, so this is ma, so this one will be f, but we're considering multiple forces, so sigma f, and this one will be the normal and shear stresses. So I use sigma here, which is the stress tensor. And the f body is basically the gravitational and electromagnetic forces we covered earlier. So nabla dot product, the stress tensor sigma. Okay, so this one will be part of the normal shear stresses. So we start analyzing from the stress tensor. So the stress tensor can be split into this. So this is the original expression of the stress tensor. So it covers the different vectors in 3D Euclidean space. So the stress tensor from xx as well, y, z, and the tau. So these are the normal stresses. So the sigma here means different stuff from the sigma here. So it's quite confusing. I thought it's the stress tensor initially. Just remember it's different. And the tau is the viscous stress tensor. So we have sigma equals negative pi plus tau. I'm missing I, but I here is mostly to consider the different directions, so to say. So it's not exactly the most important thing. Just remember. So it's just for the diagonal components. Oh, so we can see the I here. Yeah, sorry, I was wrong. And sigma equals tau for off-diagonal components, since shear stresses are directly related to viscosity, and so it follows this. So if I had to explain more, then I can just expand the previous matrix form to this. So sigma equals negative pi plus tau. So this is a negative pi, and this is the tau. So we now just substitute the stress tensor into here. So this one's the stress tensor, not the normal stresses. So just substitute negative pi plus tau, and because the divergence operator nabla is distributive, so we have negative nabla p plus nabla tau. So the I is missing here because of the direction thing I mentioned earlier. You can go search it up once again. I will not explain everything here. So now, just to get the more good-looking expression, we just assume the fluid is Newtonian, and this part is mostly because modeling again. We're doing climate modeling, so considering this only because the air is compressible, but air is Newtonian. But so we just gotta have this very nice expression here. Not the most friendly looking, but tau equals mu times nabla u plus nabla u to t's power, and plus lambda nabla dot product u times I. So this one, it can be quite confusing. It's not exactly the most straightforward. So it's the transpose of the velocity gradient tensor. It's not you just have the divergence to times itself for t times. It doesn't make sense in that way. I guess you could search this up for more. Again, I won't explain everything here. I just here to have you have an overview of the flow of the Navier-Stokes equation quite literally. So it follows with the distributive property of the divergence operator. So you substitute things in and you get this very ugly expression, but this can simplify to the previous given form if assuming the fluid is incompressible. So I didn't cover it here, but if the fluid is incompressible, then this whole thing will disappear, and this thing will transform into some better looking parts, so to say. And this part is mostly mathematical significance. If you want to stay here, you can listen, sure. Okay, so du over dt, right? So we can have del u over del t plus u dot product nabla u. So this one is what we're actually caring about if we're studying the mathematical significance. So we consider the equations to describe an average body of fluid. So again, the equation describes the motion, the trend of the fluid at a certain point, at arbitrarily small point, infinitely small point, whatever way you want it. But it's just at a point. So of course, in real life, we couldn't consider like every small point. We can measure like the velocity of and the pressure of like every small point. So we can take an average body. So in climate modeling, it's like a few kilometers. We take the average wind speed and pressure whatsoever, and we just go with that. And it's pretty much accurate enough. if not considering the carbon 6 and other human interference, but we're not going to talk about that because this is about Navier-Stokes and not carbon modeling. Okay, so we can tell that if U0 is smooth and has sufficient decay at infinity, so just because it decreases, then there exists a time a t between 0 and infinity. So t star can be infinity. It's like it doesn't matter. And a smooth solution, u and between 0 and t star. So it's in Euclidean space, and for phi it's also in Euclidean space, but furthermore, if t star is smaller than infinity, like extremely smaller than infinity, the subnorm goes to infinity as t goes to the small t goes to the big t star. So it leads to finite time blowup. So for finite time blowup, it's basically that that I explained here. U dot product nabla u is far bigger than the mu times nabla square times u, so causing unbounding growth of velocity. So velocity will just go to infinity, and this doesn't make sense. So that's why I started in the first place. So this one is the transport term, by the way, and this one is the viscosity term. So this one wants it to move, this one doesn't. So especially in tug of war, in Terence Tao's analogy. So yeah, with mathematical understanding of the inertia, you can deepen our understanding of mathematics itself greatly. And I just hope this video is beneficial for you and is informative and everything, and you just gotten a flow. I may have small points that are wrong because, come on, the other videos are kind of wrong in their own sense. You still need to study most of the stuff yourself, and including this part, which is very important, but I didn't cover it here because this is a mathematical essay, not a physical essay. So yeah, and yeah, the citations, by the way, some of them are mixed with climate modeling. If you are interested, then you can just go to these sites. Most importantly, this one. Like the more mathematical stuff are from this one. It's the most important one, and it's by Terence Tao, the goals. So yeah. Goodbye. Don't subscribe. Don't like. Just don't do it. Don't do it. And bye. Hope it has been a good time. I hope. Yeah, why am I still here?